Hello and welcome back to Calculus 3. We are starting chapter 13 on multiple integration. So we have the first lecture on double integrals over rectangular regions, which will be followed with the double integrals over general regions, which would be followed by the double integral in polar coordinates. And then finally in 13.4 we are going to upgrade to triple integration. We are going to learn new coordinate coordinate systems. Cylindrical coordinates and spherical coordinates will be studied in 13.5. 13.6 is going to be looking for center of mass, and that's going to be really cool. And then hell on earth, 13.7, change of variables in multiple integration. That one is the carpal tunnel for this chapter. So we are starting chapter 13, and the first order of business is to look into double integral over rectangular regions. So now, knowing the domain and knowing that the domain is two-dimensional is more important than ever. In order for us to understand which way these integrals work and what they do, first I'm going to mention, just in case. Oh, hold on, this is the wrong app. This one is the one that we need. There we go. Aha. So before we dig into the actual problems, I have to go back to Calculus 1 and make sure that you understand some of the most basic ideas. First of all, when I write the integral from a to b of f of x dx, I hope you're understanding that it computes the area under the curve. Now, we have two dimensions, right? Because area is meters squared or feet squared or miles squared, whatever, right? So we have to have two dimensions at present. So first dimension would be this f of x, and the second dimension would be dx. And they are multiplied. There is actually times in between, which is the reason why almost every professor is highly allergic to situations when you do not write dx, right? Because it actually provides the dimension to a problem, and it is necessary to be there. Now, if you are trying to understand this and what it means, right, you are going to have some function f of x, and then you will focus at the area between a and b, and that area will be computed by the integral that we have. Now, the way this works is we can pick representative rectangle, and that representative rectangle is infinitely thin. So this delta x, the dx, is extremely, extremely small. How small? Well, you think of very small, and then you always think of smaller quantity. So that means it's small forever, right? But still, this is a representative rectangle. And if you look at this representative rectangle, it has the height, right, h, which is actually f computed at the point, and you have delta x, which is dx. So that f of a times dx is providing area for one of those. So if you are looking at the Riemann definition for the definite integral, you would see that the definite integral is given by, and now please pay attention to this, and then I'm going to construct this so I don't have to write it 15 times. We just said that if you multiply the function, so I'll just call it f of c, by delta x, you get area of the single rectangle. And then what you do is you add all of the rectangles from I equals 1 to n. So I'm going to now call this ci because I will have multiple there. and then I'm going to send the number of those rectangles to infinity. Now, when you send the number of rectangles to infinity, delta x becomes infinitely small, because the formula for delta x is b minus a over n. So b minus a, those are the two numbers that you have on the x-axis, right, the interval. So that's going to be, let's say, 7. And then you're dividing that by the number of rectangles that you have. But the number of rectangles, we just send that to infinity. So when you divide 7 by infinity, you're getting 0. So delta x is approaching to 0. Each one of these representative rectangles is infinitely thin. Infinitely thin. And you have infinitely many of them. When they all add together, which is what the summation is for, when they all add together, they add to exact area under the curve. So it's important to understand that Calculus 1 definite integral computes area under the curve. Area is two-dimensional. Therefore, you have to have two dimensions on the left-hand side of our equation. And we have f of x, which provides the height, and delta x, which provides the width. Width times the height is the area, right? So we have that. Now, if I want to go to the, let's say, without doing any work yet, double integral of some function of f of x, and I put dx dy, well, this better provide us with a volume. Because now I have 3 dimensions inside the integral. Oh, this is supposed to say fxy. It's right, there we go. So I have 1 dimension provided by f, 1 dimension provided by x, and 1 dimension provided by y. So now this is 3D. Well, volume is 3D, so it makes sense. So I can use double integrals to compute volume. However, I can also use double integrals to calculate area. And that's very easily done by just removing the function. If you just integrate double integral of x, double integral of y, right, then you just have 2 dimensions because you removed f dimension. And then integral will calculate area. We'll get there. So now we understand, by extending Calculus 1 into Calculus 3 here, that the double integral with function inside provides us with volume. Now, if you are trying to understand this, let's draw some diagrams for you. If you're not trying to understand this, then we're just going to look at calculations later, and then you're done. So this is my XYZ coordinate system. And in this coordinate system, I am going to have some kind of rectangular domain. So this is my rectangular domain. It is very easy to find objects with a rectangular domain in this classroom. Give me at least 2 examples. Desk, very good. Give me another example. No and no. No. No, the room itself, good.
This piece of paper.
No. So the room itself, the desk, and the printer over there, right? Yeah, it's very thin, so I'm just going to call that 2D. So, guys, I'm not going to draw the printer, but think of it as, right, we have some kind of a shape on top. That shape, actually, you know what? I'm going to do some some curving over here. So let's go. Whee! So it's a weird shape on top, but what's important is that you have a rectangular domain. It's a rectangle in the domain. Now, what I'm going to do is I'm going to now define a representative French fry, right? So if you look at your x and y axis, we can come up with this little guy that will extend all the way to the top. Now, I call this representative French fry because that's what it is. You're going to have something like that. And I need to call your attention to its dimensions. Along the x-axis, you have dx. Along the y-axis, you have dy. And the top over here is given by f of xy. So I hope that you see that all we did is we went dimension up by adding y from calculus 1. So it makes sense to say I have the integral for the dy, I have another integral for dx, and that provides you with 2 dimensions, and then f of xy inside. Now, I will color code this. The integral outside corresponds to the dx, and in green, the integral on inside corresponds to dx, which is on the inside. So the outer is, in this case, dy, and the inner is dx. And I'm also going to put a, b, c. Now for dx, I like to put a and b. And for dy, I like to put c and d. These are definite integrals. So this is definite integral. Because we have limits of integration. We can also have the integral that is dy dx. Keep forgetting the y over here. In which case, a, b, c, d. And that's still going to give us volume because 1, 2, 3 dimensions, right? So this is our integral that we are going to consider. It's called the double integral because we have 2 integrals in there.
So when we go to integrate, we just do it like we used to, but then
yes.
AB first and then CD.
No, in this one you always do the inner first. So you do the inner first, okay. And then when you get the answer for that, you integrate that with the outside.
Would it be obvious, like when we were doing these problems, which one would go first?
Yes, because you have dy dx or dx dy.
I see.
They are.
Oh, yeah.
They are interchangeable. I mean, once you write them and you're solving the problem, they are not. But you can set up one way or the other. That's all the part of the lecture, so we'll get there. So let's first solve one of these guys. So let's say you have 3 to 6, and then 1 to 2 of x squared y dy dx. So this is the first integral we are going to compute. So we're looking at this thing, and as I said, do the inner integral first. Now you are taking the derivative, the integral in respect to y, which means that x is going to be a constant, and the y is the variable. So you're integrating y, keeping x squared constant, and just copying that one. So we're going to copy the outer integral 3 to 6 because we are not doing anything with it. And the inner integral becomes x squared y squared divided by 2, computed from 1 to 2. And we still have dx that we didn't use. So if you look over here, the inner integral, right, guys, just eliminate like the layers of onion, okay? You eliminate the entire layer of onion, and there is still a whole onion layer inside. You eliminate that layer of onion, and then there is another one inside. We can chain 15 of these integrals if you want. Your job is to focus on the most inner one, right? So you take all of the other layers off and just have a calculus 1 integral to deal with. Now this one is variable is y, so integral of y is y squared over 2, and x squared is a constant that you copy. And then you have the 1 to 2 limits to compute. Compute that and then hit it with the x integral. Yes?
Since fxy equals fyx, if you could do dx first, you just have to switch the integrals, correct?
Yes, and that's only correct for rectangular regions. But yes, we are going to do that.
Are we not doing rectangular?
Yes, we are.
Oh.
So
So when you plug in 1 to 2, you're only plugging for y.
yes, and she started talking, so I didn't get that.
So this is correct for rectangular regions.
You can swap them, yes. For other ones, yeah, it will be fun to switch them.
Oh, okay.
It's coming up. So I still have my integral 3 to 6, which I haven't done anything. Now, since I computed a y, we have x squared over 2, and now we have 2 squared minus 1 squared, right? Those are the y's. And I still have dx. So 2 squared 4 minus 1 is 3, so we have 3 halves x squared dx to deal with. Now integrating this becomes 3 halves x cubed over 3. 3 is die. Integral computed from 3 to 6. So this is 1/2 times 6 cubed minus 3 cubed. Now, if you don't want to cube a 6, what you have is 2 times 3 times 2 times 3 times 2 times 3 minus 3 times 3 times 3. So clearly you have 1/2. You can factor out 3 cubed, that's 27, and you're left with 8 minus 1. So 8 minus 1 is 7, so you have 27 times 7 over 2. If that makes you happier. So 140, 189 divided by 2. Done. Domain. You should be focusing on this stuff, but that's okay. Domain is everything as you are trying to set up integrals. You have to have a skill of figuring out the domain or the region over which you are integrating, and in this case it's the easiest case. So I'm just going to put a random rectangle here and the random x-axis and y-axis. I just placed this in random. Now you have to draw the same thing if you're going to use my numbers. So since this is what I put up, then this number over here must be 3. This number over here must be -1. This one has to be -2. And this one must be 5. So dx is in between -2 and 5. And dy is in between -1 and 3. So those are so now if I want to integrate, I will have double integral some function xy over here, and now we have a choice. Now I'll write that as a theorem, but we have a choice of writing dx dy or dy dx. So let's say you put dy dx. The outer integral has to be x's, so that's -2 and 5, and the inner integral has to be y's, which is -1 and 3. So what are the limits of integration? Limits of integration are the numbers that are bounding the rectangle, which is your region of integration. So very simple. Next section, not so simple. You're going to have different functions, parabolas and things. And that's going to introduce some headache, but that's next section, so don't worry about it yet. So now I'm going to write this theorem, which says the integral AB integral CD of f of x dy dx is the same as the integral CDAB of xy dx dy. You are allowed to swap order of integration. So we are allowed to swap the order of integration by simply switching dx dy and limits. Okay, now in blood, this does not work for non-rectangular regions. Means that tomorrow in 13.2 you will not be allowed to simply switch them. Now you can. So if you have rectangular region, all of your limits will be numbers, and you are allowed to switch order of integration. Next section will have functions in the limits, and you can switch those. Well, you will be able to switch them, but there will be a lot of other witchcraft that has to be done before you can actually switch order of integration. So order of integration is going to be actually a problem to do in the next section. Now, just swap it, and you're done. So, let's take a look at some basic ideas. If I have rectangular region right here, so this is at 1, 2, 3, 4, 5, 6, and 7, and then 1 and 3. So if I have a rectangular region, now what I can do is I can calculate the area of that region by using A times B formula, and that would be simply 6 times 2, and we will get 12. This is what you do when you are in elementary school, I guess, or middle school, whatever, right? Then you get to Calculus 1, and in Calculus 1, you say, okay, this is the integral from 1 to 7 of the function 3 minus function 1 dx. You have y equals 3 constant function, that's the horizontal line, and you also have y equals 1. It's a top function minus the bottom function. This is a simple Calc 1 area between two curves. Top curve minus the bottom curve, and we have 1 and 7 limits of integration because we go from 1 to 7 on a dx. What you have is integral of 2 dx, right, 1 to 7, and when you compute this integral, you get 2x computed from 1 to 7, which is 14 minus 2, and you get 12. All right, this is good when you tutor those middle school students, right? And you say, okay, area is A times B, 6 times 2 is 12. They say why? Well, now you have the backup. If it's still not clear, you immediately say, or I can show you the Calc 3 version of it. The Calc 3 version of this would be the double integral. Now, I told you that you don't get to put the function in because the entire rectangle is going to be explained through limits. You have the y limits to be 1 or 3, so that's the first integral we are computing, and the outer integral is dx because we picked 1 and 7 on the outer integral. So now, when you integrate in respect to y, you are integrating 1. So integral of 1 is y. So we are going to have 1 to 7, y computed from 1 to 3, dx. So we computed the inner integral first. This is now converting into Calc 1 integral, as you can see, because you have 3 minus 1 here, and that's exactly what you had as a setup, right? And then I'll just put 3 dots over here equals to 12. If it's still not clear, just do it the other way, because we can. Switching the order of integration obviously switches x and a y. Then you will calculate the x integral first. So the integral of 1 is x from 1 to 7. Still dy to do. Integral 1 to 3 of 7 minus 1 dy. So now you have to compute integral 1 to 3 of 6 dy, which is 6y computed from 1 to 3, which is 18 minus 6, which is 12. What I just did is I solved the same thing 4 different ways. Right? We had length times width, basic formula for rectangle. Exactly. And then we have the Calculus 1 version, area between two curves, and then we have 2 of these Calc 3, depending on which way you set these guys up. And now we can take a look at some other situations. Let's look at some problems from the text. Maybe I should write, I should write. Let me just show you briefly from the book on page 965. We see this representative French fry at work. So if you have a very thick French fry over here. You see that this grid is 4 by 4, so this one contains only 16 French fry over here. You see that the top over here is very rough, right? Hold on. We have, so as you cut each fry into 4 fry, you're getting better resolution, right? So these are very, very, very thin. But as you can see, the shape on the top is becoming smoother, right? Because it's better resolution. Technically, to improve the resolution, if you take your old calculators, if anyone has TI 8384, there it is, right there, right? The resolution on that screen is terrible because pixels, right, which is not divisible any further, pixels are very, very large in comparison to cell phone screen, which has a very, very small pixel, right? So the resolution of that screen, let's say, is 300 by 300. Resolution on phones is thousands by thousands. So that's why picture on the cell phone screen is extremely, extremely sharp, because you have a lot of these, lot of pixels. So now, as I said, as your French fry, representative French fry, which is dx by dy in the base, as those become infinitely thin, and we have infinitely many of them, they give us the exact area. And we see that we are taking the height of those French fry times the area of the cross section of each French fry, adding them all. Delta goes to infinity is the same as n going to, delta goes to 0 is the same as in n going to infinity. So you send all of those to infinity, and you have the exact volume. So let's see some problems from the homework. Oh, and before we do the problems from the homework, one more definition here. The average value of the function is given as the 1 over the area times the double integral over the region R of f of xy dA. So this is the average value. And you know what? I think I still owe you the explanation a little bit on this dA, just in case. So let's write it down. dA is equal to dx dy, or dA is equal to dy dx. So that's what it means to have dA. So if I have the integral, so this is just now notation, talk about notation. If I have a double integral over the region R for, let's say, xy minus sine x dy dx, I can just short write this as xy minus c sine x just dA. That's just notation. So don't freak out. All right, we have lots and lots of interesting problems. So let's see. Something nice. So pick something 17 through 25. We'll do 2, let's say. 17 through 25. 21 it is. So double integral over region R of square root of x over y dA and your region is given by all of the points x, y, such that x is between 0 and 1, and y is between 1 and 4. All right, so if you need to visualize your domain, you will draw this. X is between 0 and 1, and y is between 0 and 4. So, this is the region R. Nope. It's the region. So now, but you already see these are your limits for dx, these are your limits for dy. And since it's in rectangular, right, you can write it in any order you want. So now we have a double integral of square root of x over y. And now you can pick dy dx or dx dy, it doesn't matter. But then you have to be careful where you put the limits. So I put dx on the outside, so 0 and 1 goes on the outside. And since dy is on the inner side, we have 1 to 4 on the inner side. So we are supposed to integrate first in respect to y. I'm going to rewrite this problem before I actually do any integration, because it's easier if you rewrite it. X is in the numerator, so that's x to a half, and y is in the denominator, so that's x to the negative half. That's what I said.
Yeah.
So x is in the numerator, and it gets positive 1/2, and y is in the denominator and gets negative 1/2 as the exponent. So now we are going to integrate in respect to y first. So copy integral 0 to 1. Copy x to the 1/2, that's constant. And integrate y to the 1/2, so that's y to the 1/2 divided by 1/2. Computed from 1 to 4. And we still have dx to deal with. Zero to 1. Now we have x to the 1/2. 4 to the 1/2 is 2 minus 1. All of that divided by 1/2. Still have dx at the end. So 2 minus 1 is 1, divided by 1/2 is 2. So now I have to integrate 0 to 1 of 2x to the 1/2 dx, which is calculus 1. So we have 2 times x to the 3/2 divided by 3/2 from 0 to 1. This becomes 4/3 x to the 3/2 computed from 0 to 1. Great. 4/3. Meditate on this. I'm sorry? Yes, but that's 14.4. We have ways to go. It's a learning outcome, yeah? No. Flux is flux. We are going to study flux in separate section. All right. So let's take a look at another problem. So this problem, as you can see, we have the integral, we have the region. Region is only showing the domain. We are integrating over the rectangular domain, i.e., domain is rectangle, all right? Believe it or not, that is going to change its meaning as we keep, like rectangle will mean more things than just rectangle as we go on to the next lectures. But we'll leave that for then and there. Let's take a look at another one. Range is Z, but we never did. Oh, 17 to 25. I was fixated on 22 because of the very important feature. Yeah, that's why. So problem 22 has a very specific, interesting feature. Yeah.
Does the same thing happen with the integrals where you have to like when we did was it e to the x or cosine we had to like integrate it twice and throw them in the
No.
side? No.
Sorry for disappointment, but no.
Oh, definitely do that, right? Yeah.
Why?
Because then you don't have to do that.
So, all right. Liz already figured it out. Yeah. While you were talking. Well, why? Were you blubbering?
No, I was silent.
Oh, okay.
I don't hear all.
0 less equal than x less equal than the square root of pi over 2. And the y is between 0 and 1. So that's our region. And now we put our integral. So we have xy sine x squared. And now which one do I integrate out first? Y. Exactly. So now x is on the outer, so limits for x go on the outer. And y is on the inner, so 0 and 1 go on the inner. Integral 0 to root of pi over 2. And now when I integrate, x sine x squared is a constant. And I'm integrating y, so I get y squared over 2, computed from 0 to 1. dx. I haven't used that dx yet. So 0 square root of pi over 2, x sine x squared. And now I have, when I plug in 1, I get a half. When I plug in 0, I get a 0. So you know what I'm going to do? I'm going to kick this 1/2 outside. Yes, u sub. Very good. So u is equal to x squared. Du is equal to 2x dx. I do not have 2x, so I will have to fix that. I will plug in 2, and I will also plug 1/2 outside to balance it out. So now I have 1/4, half times half, integral. Inside I have sine u du. That's basic calc 1. And I still have to deal with limits. So plug in 0, which is 0 squared, we get 0, so the bottom limit remains 0. Plug in the square root of pi over 2, and that's squared, that just gets pi over 2. I change the limits of integration so that I don't have to go back to x variable and then also deal with the square root of pi over 2. I changed my variables, and now I have a much easier integral to deal with.
So did you put that back into the first one?
Nope, this is it when we compute.
To test for you.
No. So 1/4, we have negative cosine pi over 2 minus negative cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1, so the answer is 1/4. Cosine of pi over 2 is 0. Cosine of 0 is 1. Negative and negative is positive, so the entire parenthesis is just positive 1. 1/4 times 1 is 1/4. Double integrals are fun, right?
Yes. Now. Now I agree.
Good. All right, so here's one for you.
I'm good, thank you.
I wasn't asking. Find the value. Sorry, find the average value for e to the negative y on the region R given by xy points such that x is between 0 and 6 and y is between 0 and ln 2. You have the formula over here. The formula says average value of the function is 1 over area times the double integral. So 1 over the area times the double integral of f dA.
Is area B
Area of the rectangle of the region. You have that in the region, right? It's not. Now, guys, please always observe if the number of dimensions makes sense. If you're banging your head on the exam, trying to figure out if the formula that you are trying to recall is correct, at least you can verify it dimensionally. So I'm not looking at something and going, holy nightmare, why do you have 17 dimensions? Look, double integral of f. Well, double integral of f, that's 1, 2, 3 dimensions. Dividing that by area, which is 2 dimensions, gives you a single dimension. This is a one-dimensional, right? It's just function. So that's 1 dimension. So over here you have 3 dimensions divided by 2 dimensions. Well, 3 minus 2 is 1. So A is the area of the rectangle. A equals the rectangle. The domain. Makes more noise. Oh wow, now you're singing while doing math. That's progress. It's 1. So you integrate it, and you just get x.
X, you have a constant, so you just throw in x. Like, try to simplify it.
That never happened before?
Well, no.
Never?
No.
How long you had this secret? That was the first thing that crossed my mind.
Oh, that's what he said, right?
Yeah.
What happened?
His sticker on the phone.
So funny.
Sticker says. I have to sit right now.
Are you supposed to get a number for this?
Yes.
Well.
If you got 7, it's wrong.
I got 1 over 2 and 2.
I got -1 over.
I just got
I don't want to talk about it.
I lied, it's not negative.
All right, let's so. I mean, you can always take it outside because we all have different answers, but maybe we can resolve the matter this way. Right. Some goodness shines, right? Reason. So first I need to deal with the area of the rectangle, and that's 6 times ln2. That's what it is. So average value of the function is going to be 1 over 6 ln2 times the double integral of e to the negative y, and then you can do, if you want, let's do dy dx. So x is on the outside, which means 0 and 6 on the outside, and 0 and ln2 on the inside. I have 1 over 6 ln2, integral 0 to 6. The integral of e to the negative y is negative e to the negative y, computed from 0 to ln2, and I still have dx. 1 over 6 ln2, integral 0 to 6. Now, when I plug in ln2, right, I'm going to write this as negative 1 over e to the y. So when I plug in ln2, ln and e will cancel and just get negative 1/2. And then we have minus. When I plug in 0, e to the 0 is 1.
Yeah, so it's negative 3.
So it's plus 1. I have a negative from the formula and negative in front of e. Dx. So 1 over 6 ln2. Integral of just 1/2 dx. Well, that half goes outside as a 12. 1 over 12 ln2.
I swear it's a negative 1.
And then I have to...
Isn't it a negative 1?
It's negative 1, but it's already minus.
Minus in the formula and a minus over here.
Negative
Get plus.
0 is negative 1, but you subtract.
So it's 2 negatives gives you a positive plus 1. Thank you.
Yeah, thanks.
The only thing I know how to.
Way to ruin it now. After all that good work. So yeah, you're right. 1 over 2 ln2. Boss.
Oh.
What? No, not shocked. I'm trying to be enthusiastic.
Okay, one.
All right, one more and we're done. English, man, English. Y cubed sine xy squared dA. Region R is given as all points xy such that 0 is less than x less than 2 and y is between 0 and again square root of pi over 2. Boring. That's problem 30.
Yeah, the only thing is, like, if it's a saddle point, no, you just do FX. Yeah, FX. I don't know if
I did the X first. I don't like where I did. I'm just 3 weeks. 2 weeks.
Yeah.
But I'm engaged with someone, so I don't know related. Also have a showing up
So did anyone run into any problems?
Oh my god. So rude.
That's his job. Everyone is nice. Just no. Bland. Oh, yeah. You gotta evaluate. You gotta evaluate.
Oh.
Those things. Is that a face palm?
Yeah.
Pain is the best way to learn.
Exactly. They took that out from education. So I don't think
I don't know, yeah.
this is
Stop, I just started. But like, I'm actually confused.
I hate this one.
When you integrate this and there's still a y there, you just like,
I hate it. Terrible.
because then you can't stop. You leave. I was gonna do y first, or no, I was gonna do x first because I didn't want it to be a multiplication thing now, but it's not.
X works.
X first or y?
X.
Why did I do it instead of y? No, but like in my head, I was thinking it should be the other way.
All right, so what's interesting about this problem?
The sign part sucks.
So what's interesting about this problem?
What?
You guys eventually want to go home and have dinner, I hope. I mean, I can stay till they chase us out, which is generally like 10:15. So that's now 3.5 hours if you keep stalling on answering.
Oh, stalling? I'm not stalling.
Oh, you just don't know.
I just don't. I tried. I gave it the best that you could try.
So the only way to integrate polynomial times sine is to do integration by parts.
Oh.
And you have to do integration by parts in this case 3 times to actually kill y cubed.
Oh, I didn't think you could.
So it wouldn't be nice to do integration by parts in this case because it's just a lot of effort for no reason. If we can maybe solve the problems quicker by integrating x first, right? So let's try to make this problem simpler by having dx integrated first and then dy. Now x coordinates are 0 and 2, so that's limits are 0 and 2, that's on the inside, and then 0 to square root of pi over 2 on the outside. So what do we get? The only thing that I need to integrate here is sine. I get to copy y cubed because I'm integrating x. When I integrate x out from sine, I will get negative cosine xy squared divided by y squared. And then I compute that from 0 to 2, and I have dy to deal with still. So, if you remember that the integral of sine ax dx is negative cosine ax over a, right? If you know that shortcut formula and you don't have to do the u sub for it, then you see that this y squared is actually that constant a. So you have sine ax, except your a is y squared, and it will be negative cosine xy squared over y squared. So now we are going to compute this with number 2 and 0. So integral 0 pi over 2. This will cancel, and I will just have y. Yay! As a negative in front of the integral, and I'm just going to deal with the cosine of 2y squared minus 1, cosine of 0, right? And I factor out minus in front. I still have dy. Is this bueno? Cosine of 0. Cosine of 0 is 1. And then it's negative because in the formula, right, it's f of b minus f of a. And then the negative I factor in front of the integral. So now, I'm going to take this negative and bring it back inside and swap the order inside the integral. Because I can. I don't want to drag extra stuff. So this becomes y minus y cosine 2y squared dy. The first integral is a joke. That's y squared over 2 from 0 to square root of pi over 2 minus, and now for the second integral, well, we have u sub. U equals 2y squared, du equals 4y dy. I don't have 4y, so I have to fix that, right? So it's going to be a 4 1/4. So that quarter goes in front. And I have integral of cosine u du. And I have to deal with limits. So lower limit was 0. So lower limit remains 0. And u2 is 2 times the square root of pi over 2 squared. This dies is just pi. Okay? That was the next step. So now when I plug in pi over 2, I get pi over 4 over here. Right? Square kills the root, and then pi over 2 divided by 2, half of pi over 2 is quarter. Minus 1/4, integral of cosine is sine, so sine u from 0 to pi. That's all 0, and the answer is pi over 4. Right? It was obvious since the start. I'm sorry? Over here, when I plug in square root of pi over 2, square kills the root, and then half of pi over 2 is pi over 4. And then the second half, we get sine. Sine of 0 is 0, and sine of pi is 0, so they both die, and we have just pi over 4 at the end. Well, that's that. I hope you're not disappointed or anything.
I was expecting a little more.
Tomorrow after the exam, we open the gates of hell, so don't worry about it. It's just a peek, not all the way.